function and it maps it to some number, right? So like 7, right? So we've got,
It's got to be 7, right, Josh?
yeah,
I have a student that I needed to make all my I felt like it was useful to make all of my times at which I imposed initial data in 334 to be the number 7. Long story. Yeah.
so it's a map from functions. So it's some map from functions to the real numbers, right? Yeah. So the easiest way to do this. So an example of this would be arc length, right? Between 2 points, right? That would be an example of one of these functionals, right? And then you could, what do you do, right? You take some function position, right? So some like x is a function of t, and then what's the arc length formula? It's like you integrate dx dt, you know, like something like that, right? Dt. Really, we might want to think of it. It's more sort of, we might want to think of it as a parameterized function. Have you taken multivariable calculus?
Yeah.
Yeah. Okay. So you want to think about this as probably more as like a parameterized function, like dy dt squared dt squared, right? So, and then let's say you know your starting point is some x naught y naught here, right? And then your final point is some x final, y final, right?
Yeah.
And then you want to find what minimizes this arc length, right?
Okay.
What's the answer going to be?
A straight line.
A straight line, right? Yeah. One of the ways you could prove that is using calculus of variations, which is so it's like doing calculus on functions of functions, right?
Okay.
Does that make sense at all? So what you do is so a lot of these, if you notice, like arc length has a form where it's like you're integrating something, some function of the function, right?
Okay.
And some function of the function, and in particular, it's also a function of the derivative of the function, right? Because this arc length is a function of your derivative. So now in physics, so in particular, right? Let's call it like f of t equals the integral from like, I don't know what you want our first time to be 7. 7 to 8, right? So just for Dr. Glasgow, of some, I'll suggestively call it an L, and then this would be f of t, and then the derivative of f of t, and it could depend on t too, dt, right?
Okay.
And then now, it turns out that the thing that that is a critical point of this functional will be whatever f satisfies the equation we have written up here, d dt partial L partial f prime equals partial L partial f here, right? Turns out that will be the thing that is the critical point. That'll be the function that is the critical point of this functional.
And it might be that there are multiple critical points for certain things, but
Yeah.
a lot of times there's just one, and that's enough.
Yeah.
So
And-
sorry.
No, go ahead.
I was gonna give an analogy. So like you can take a particle and put it in some, electric field and watch how it moves, right? And in fact, you could take Newton's laws, and if you know how the electric field puts a force on that particle, you could determine the path it'll take through space, right? The weird thing about what we're doing here is we're actually starting with any path through space, and we're saying which path through space actually minimizes this particular integral that we're looking at right here. And it turns out that those end up giving you the same answer, and that's the principle of least action. We call that integral up there, action in this context, and we're trying to minimize it, right?
Yeah.
And so what's weird is we're like, there's two different seemingly completely unrelated things that are actually kind of the same. So like determining how, this particle will act under force and move through space is exactly the same thing as minimizing this weird integral by choosing different paths through space. And in fact, that path that you end up with is the path the particle would take in physics, right? So super weird.
Yeah, no, exactly, that's
And
exactly
then it
right.
turns out ends up being kind of like the niftiest way to even quantize at one point. I haven't learned that technique yet, but
Yeah, so it turns out the Lagrangian, so as he was pointing out, the action is and it comes from a specific choice of this function that you're integrating over, and turns out the one that works really well is like the T, this is how I learned it originally, was T for kinetic, because I don't know why. So it's the kinetic energy minus the potential energy.
Just do K minus P, that's like no one does.
And think like, maybe like
V
electric
minus
potential
U.
voltage, I don't know.
Yeah.
I don't know why they used a V,
Well,
but
probably
yeah.
T for like thermal or something like that.
Maybe.
I assumed it
But
was
so-
just how you said kinetic in some other language.
That
That's-
also
that's-
in German maybe?
that's what I'm
Bro.
thinking.
Yeah, that's
You
probably-
threw it.
Yeah, so it turns out if you minimize the integral of the, so if you choose your Lagrangian, so you minimize the integral, so S is the integral of your kinetic minus potential energy, this is equivalent to Newton's laws.
Yeah.
It's the same thing. And actually, as Dr. Glasgow was pointing out, when you go to quantum mechanics, it sort of seems like it's harder to think about forces for fundamental particles, but you can still think about energies and
Right.
things like that.
In fact, since you take in 222, the things you work with are not forces at that point. You always work with what the wave function looks like and what the potential energy